folks. Welcome to Rational Science. And I'm on the road. Last week I had a big glitch, a power glitch here where I'm at, and didn't recover for another 2 hours. And then it went down again just in case. And the next day it went down again. So I hope I don't have a technical problem today. Anyways, we're going to talk about the electron today. You thought the proton was a pretty big problem in quantum mechanics. Forget about that. The electron is really the darting quantum mechanics. Okay, together with a photon. Photon and electron are more or less both in there. Anyways, in order to get to the subject matter, let me start with some introductory quotes by the founders of quantum mechanics. Here's the first one. His name was Niels Bohr. What does he have to say about quantum mechanics? Well, he said the following. He says, there is only an abstract quantum physical description. Abstract description. That's all they have. That's all that quantum is. There's no explanation, no mechanisms, no causes. It's an abstract description, and it's a mathematical description. It is wrong to think that the task of physics is to find out how nature is. Physics, meaning mathematical physics, meaning mathemagics, right, concerns what we can say about nature. That's all they're talking about. That's all they can do. Everything we call real is made of things that cannot be regarded as real. Nothing exists until it is measured. Now, are those some prophetic words or what? Yeah, and one of the big problems of quantum mechanics, of all the mathematical physics, is that they never define what a thing is. They never define what an object is, what a medium is, what a body is. They never have a word. You know, you don't have a single textbook of physics on the planet that begins by defining what an object is, what a thing is. You would think that, you know, that's the first word that should be in every textbook on the planet. Physics textbook, right? Because what you have is you can't do physics without an object. You need a thing that's got to be moving. If you don't have a thing and you only have motion, what's moving? A spirit? You know, and this is the issue. They have all these concepts that are moving. The field, energy, mass, charge. Those are not physical entities. Those are quantities, right? So we have a problem because there are no physical objects in quantum mechanics. Here's another fellow, buddy of Niels Bohr. His name was Werner Heisenberg, okay? And he said the following. He said, the natural laws of quantum theory no longer deal with the elementary particles themselves. Quantum mechanics has led physics, or physicists, right, far away from the simplistic materialistic views that prevailed in the natural sciences of the 19th century. Primarily the issue of the ether, right? That's what they got rid of, or they thought they did. The most important step was to see that our language is not sufficient to describe the situation. In such a world as the path of the electron, they are quite understandable when you have to do with stones. But when applied to electrons, they really don't mean much. The difference between elementary and composite particles has disappeared. Okay, so like a proton and made out of quarks, that's what he's referring to. Even though he wasn't from the day, well, he kind of was in the days of quarks, right? He died in '76. He said no unambiguous answer could be given any longer to the question about what these particles consisted of, since this question no longer has a rational meaning. In mathematics, in mathematical physics, right? And that is no doubt the most important experimental discovery of the last 50 years. In other words, yeah, he was probably talking around the time of his death, because 50 years, you're talking about 1926, 1925, thereabouts, when quantum really took off. That's when they started doing all the math, Schrodinger's equation, the Born cloud, etc. And this is what Max Born had to say about that. A little later, I think it was 1962, 68, thereabouts. And he said the following. He said, since the development of special relativity, theories using a substantial ether fell out of use in modern physics and were replaced by more abstract model. The problem is that, what Born had to say is that Abstract is the opposite of physical. Okay, and so we should call them abstracists, not physicists. Okay, and he said, I am now convinced that theoretical physics is actually what? Philosophy. Okay, so these people don't do physics, they do philosophy. They just come up with whatever explanation comes at the top of their head, and it's always irrational. It's always an irrational explanation, meaning you cannot picture it. You cannot imagine what they're saying. And they cannot put it on the screen, because whatever they put on the screen doesn't match what they're saying. You know, what are you going to put for field? What are you going to put for energy? What are you going to put for mass? What are you going to put for charge? Number? Is that what you're going to put on the screen? Represent it with a little ball? Is that the way it works? You know, so this is the problem. They're doing philosophy. And last guy I'm going to quote here, his name is Richard Feynman. He said, I think I can safely say that nobody understands quantum mechanics. And he says that the more you see how strangely nature behaves, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics, mathematics, has given up on that. And he said two things there that you got to keep in mind. When he says they've given up on that, meaning it used to be part of physics, okay, but they gave up on that. They said we can't explain anything. That's one issue. The other issue is they cannot explain it. So to this day we have no explanations. And yes, it used to be part of physics, but they've given up on that. They don't do that anymore. They just do math. They call it physics. They continue calling it physics. That's the status today. And so what's the problem there? Primarily is that they don't have an object in front of you. They're not doing physics at all. They're not simulating their mechanism with a real physical object. I don't care if they use an analogy. An analogy is okay, but the analogy has to stand for something. You know, you can't represent space-time, a concept, with a physical object. You cannot represent a number, such as energy, which is a number, a quantity. You cannot explain field, which is a bunch of numbers, right? You cannot represent that with a physical object. You cannot put a thing there on the screen and say this is a field, or this is energy, or this is mass. You cannot do that, because those are concepts. It's like saying you're going to represent love with a heart again, you know. And yeah, it's an irrational thing. You cannot, not in physics, you cannot put a heart and say this represents love. That's not an analogy. Okay, you can say a fishnet represents something, like, you know, a canvas. So if you're going to talk about a canvas being weighed down, like in the case of relativity, you can represent that with a fishnet. But they don't have what they're representing is 4 number lines. You know, that's those lines that you see there, those are number lines. And they're bending the number lines. They say, well, you understand the mechanism there. We're weighing down the number lines. We call that a canvas, a fishnet, whatever, a trampoline. What is that? And one fellow, a visitor to the site here, he synthesized it quite well, and I liked what he had to say, so I'm going to reproduce almost everything he said. He said, the word physics is only relevant to the classical world in any sense of... The word physics is only relevant to the classical world in any sense of a physical object. But even then, the concept of anything that we call physical is really on shaky ground. So no, we don't appear to have anything in the universe that is represented by the classical concept of something physical. There is nothing physical as far as discrete object is concerned. And he's saying exactly what, you know, the way it is in mathematical physics. There are no physical objects. All there are is abstract concept, mathematical concepts, which they represent with physical objects. He says, in an invisible but measurable is an invisible but measurable force physical? Is a magnetic field physical? Well, hopefully it is physical. Here you have 2 magnets that I always show, right? And you say, well, there's a force there. Yeah. And why is he saying that there's nothing there? There's nothing physical? Well, because he can't see or touch them. He says there's nothing here. Yes, there is something here. The problem is you can't see or touch it. That's the problem. A field is mediated by something, and that's something that they had to discover all these years. That's what they never did. And so he says, this is the closest there is in the universe that is representative of the word physical. It is just a force in an empty void. Absolutely not. Force, field, energy, all those are mediated by physical objects. Otherwise, you are doing black magic. You're doing action at a distance, which is the scientific version or term for black magic, witchcraft. That's what you're doing. So you better put a physical object in there, and you better not define the word object as that which you can see or touch. Not all objects can be seen or touched. Among them, the most important example, air. Made out of atoms. Hopefully there's something there. You feel it, you know, something's going through your nose, but you can't see it. So because you can't see it, there's nothing there. It's a spirit that goes through your nose. So this is the problem. Yeah, there is something there, but you can't see it. Okay? And you can't touch the table that's on the other side of the universe. So hopefully the table is always a table everywhere. Okay, and here you have same fellow. He says, he goes into the word energy, which is what he thinks everything is made out of. He says, our classical brain has trouble with that concept of the absence of any truly solid object or solid anything. The only reason we don't fall through the floor is because of the non-material forces that resist it from happening. It's all just empty space or a void. So he really thinks he's going to do physics with nothing. He thinks the reason you don't fall through is there's nothing there holding you up. He really believes this because that's what quantum mechanics has told him, that everything's just empty space or just forces or energy. And he accepts that those are concepts, so he can't picture any physical object. So he says there's no physical object underlying any phenomenon. That's his conclusion. And that is the conclusion. That's the way mathematical physics operates today. So he said matter is just another representation of energy, a non-material force. Now energy hopefully has something physical in it. Energy is the concept, is the mathematical description of that thing. But you have to identify the thing which is invisible and intangible, called energy, or that underlies energy, the concept of energy. So everything that there is in the universe is energy. Non-material in the classical sense, and forces like the field of a magnet, also non-material. So they're doing everything with spirits, with angels, with all these ghosts. There is no true physical universe. In truth, that would mean physics, study of physics, is an incorrect term for this study of how our universe works. There I agree with him. You can't call that physics. That is not physics. And just in case, we have good old Richard Feynman again. He says, it is important to realize that in physics today, mathematical physics, we have no knowledge of what energy is. And the problem with what Feynman says is that, energy is a concept. So he was talking about a what. Now you can't say what is energy. That's an irrational statement. Okay, because energy is not a what, not a thing. Only things are what's. Okay, so this is the problem. Energy, the capacity, the ability, and those are concepts. Concepts we define, objects we point to and name. Okay, so if you want to present an object in physics, you point, say table. You say rock, tree, and so on. That's the way it works. And people see the object, understand the noun, understand what that word refers to. That's the way you present objects in physics. What are you going to point to for energy? A cloud of smoke? And that's how they represent it, as a cloud of smoke. No, and what has happened is mathematical physics is really all math. It's gone completely into the math world for the last 100 years, and that's why they cannot explain anything. Partly because it's all math, and partly because they're representing all these mathematical concepts with physical objects, moving the object, and you're thinking, oh, they're moving the field, oh, they're moving the mass, oh, they're moving the force. And what you're really, you're staring at an object, but that object is representing a concept. That's the problem. Like the soul, what do we represent the soul with? We represent it with a spirit, right? So you draw a ghost, you draw an angel, and you move the angel and say, okay, I understand that, the soul moved. No, an angel probably moved, not the soul. Soul cannot move, conscience cannot move, mind cannot move. Okay, it's a concept. People don't always pick up on that. And yeah, so they went in the mathematical direction, and one fellow, his name is Max Tegmark, he said the following. He says, mathematical universe hypothesis. He invented this notion. He says, the MUH, mathematical universe hypothesis, posits that the fundamental nature of reality is mathematical. So he says math is the reality, okay? Meaning the universe is a giant mathematical object. Object? Maybe a mathematical concept, but never a mathematical object. What is a mathematical object? If the MUH is true, the properties of the universe would stem from the relationships between its fundamental building blocks rather than the inherent properties of those blocks themselves. In other words, he's not talking about things, he's talking about relations, okay? In other words, they compare things, they contrast things, or show them moving or whatever, one thing with respect to another, and it's those relations which they mathematize, and that's what they call physics. And so far we have no objects in front of us because they can represent all of that with point particles or points, right? And they say that's a particle. And no, that's not a particle. And I like to say that, you know, when you have an elephant, you can find out what the center of mass of that elephant is. So you have, I don't know, an elephant weighs 5 tons. You put it into a point, you say, okay, that's the center of mass of this elephant, right, of these 5 tons. No problem so far. The problem when you start moving the point, that's when they commit the irrationality. You can't move the point. The point is there, that's the center of mass. You don't move the center of mass. What you move is elephants. You got to put the elephant back in if you want to move something. And that's where they get the irrationality. You start moving points, and they say, I'm moving the elephant. No, you're not moving an elephant. You're moving a point. You're moving the center of mass. And that's irrational. That's okay in math because all you're interested in is in the motion. But the fact that you put a point to represent the elephant does not allow you to move the point. You have to move the elephant. Okay, and so the MUH can be seen as a form of Platonism where abstract ideas like mathematical structures, whatever that is, have a real existence beyond our minds. Existence is not something you measure, and it's not something that's beyond the mind. Existence we define, and it's an object that has location. So you have to have an object. There are no such things as mathematical objects and no such things that as mathematical objects that exist. You cannot say that a mathematical object exists. First, you would have to define it as a thing, meaning it has to have shape. Then you can say, you know, you can hypothesize that it exists. Okay, so where did good old Max Tegmark get all this stuff from? This thing about a mathematical universe. Well, he probably got it from this guy. His name was Galileo, and he said the following. He says, philosophy, nature, is written in the great book which ever is before our eyes. I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. The book is written in mathematical language. Mathematics is the language in which the God has written the universe. He gets it from one of his books. And where did he get that? Well, he got it probably from this guy. His name is Pythagoras, who said more or less the same thing 2,000 years before him. He says, mathematics is the language of the universe. Reality is fundamentally mathematical. This is what all these mathematicians have been doing for the last 3,000 years. Numbers are building blocks of everything. No, not in physics. Objects are the building blocks, or atoms you could say, but not concepts, not mathematical concepts. Mathematics is not just a human invention, but the language used by the universe to describe itself. No, Father Universe never went to school. Mother Nature never went to school. They don't know what mathematics is. All they do every single day of the year, every single second, is move one atom from one location to another. They deal with objects. They're known as atoms, and they move them from one place to another. That's it. That's all they do. And do they make relations between atoms, between things, objects, stars and moons and planets and so on, galaxies? Absolutely not. They don't make any relation whatsoever because every atom in the universe has only location in one frame of the universal movie. In the next frame, they all are those same atoms, right? They all have location again. That's all they have, location. And in the next frame, all they have is location. So any frame that you analyze, that you look at, only has every atom in the universe at a given location. There's no relations, no mathematics, none of that. Father Universe does not understand math. But this is what these people came up with. And he said Copernicus, well, not him, but other people say Copernicus, Kepler, Galileo, and Newton developed a scientific understanding of the universe based on mathematical principles. Yeah, so all they had is a description. They never had an explanation for anything. Not one of those individuals ever understood how this universe works because they had it wrong from the start. They thought mathematics was going to give them an insight into what gravity is or what light is, and it never did. And to this day, not a single mathematician on planet Earth, from Cambridge, from Harvard, from the Ivy League or whatever, none of those people can tell you what is out there and what the mechanisms are that underlie phenomena such as gravity and light. Okay, so here we have the AI, and it says more or less the same thing. It summarizes this thus: modern physicists continue to explore the idea that the universe is ultimately mathematical. That's where the problem is. They continue looking for math when math is the wrong tool to analyze the universe. It has nothing to do with what is math. Math has nothing to do with it. With theories like string theory and the mathematical universe hypothesis drawing on what? Pythagorean ideas. Yeah, this is what they came up with. They think they're going to figure out what the universe is, what's out there, what exists, and the mechanisms of the universe. They think they're going to resolve it through mathematics, when mathematics is the wrong tool to apply to the question we're asking. We want to know why, this falls to the ground. Why do I need to know any math? Why do I need to study any, or, understand any equation? Why do I have to invoke numbers to explain the mechanism of what causes this to fall to the ground? That's gravity. That's the only experiment we ever needed. And yes, hopefully, whatever is here or here, pushing or pulling, is invisible and intangible, and there had better be something here. Otherwise, you're introducing angels. You're introducing action at a distance. You're invoking black magic, voodoo physics. You're saying that from afar you can move things around. Telekinesis. Absolute nonsense. None of that happens in physics. Only in the minds of religious people who are spiritualists, and they believe that things happen only because, they happen. And then just, I don't see anything there, so the reason the spoon fell to the floor was that, there's some kind of spirit. Or they describe it and say, well, this is how fast it fell. Yeah, that doesn't tell me what caused it to fall. And that's where we're at today. We have no explanations for those phenomena. Here we have good old Neil Tyson. He's going to tell us something which he likes to say constantly, and he says the following. Listen to him.
The universe is under no obligation to make sense to you. What that means is your 5 traditional senses. They're not as good at contemplating infinity. You can't intuit infinitesimal. They're things that are impossible for us.
So he says, the universe has no obligation, Father Universe, right? He has no obligation to make sense to us. Okay, and here he says it again, just in case, he likes to say this in every show that he's in. He thinks he's very smart for saying this, right? Here he goes again.
The universe is under no obligation to make sense to us. It's the observations that matter, even if they conflict what feels right to you.
Okay, so what is he saying? He's saying the universe, Father Universe, doesn't have to make any sense to us. What is he saying? He's saying that the mathematicians are the representatives of Father Universe, because Father Universe only speaks in mathematical language. And so they are the priests who interpret the universe for us, right? They study all this math through 10 years or whatever, and so they say, well, we represent Father Universe, and Father Universe doesn't have to make sense to you, meaning that the mathematician doesn't have to make sense to you. Okay, so they're saying they're appointing themselves as the priests that represent God, the God of universe, universal God, and they say we represent him because he speaks our language. He's the mathematical language. And so if you want to understand Father Universe, you got to go through us, and we explain it to you. We give it to you, all these mathematical descriptions as best as we can. And if you don't understand us, well, it's because you're not understanding Father Universe, because he doesn't have to make sense to you. That's the way they put it. No, this is very simple. I don't care about Father Universe or about your God, okay? You, the presenter, has to make sense to me. If you don't make sense to me, you're an irrational individual. Okay? In other words, if you can't make sense of what you say, you're an irrational individual. And of course, if you cannot put your theory in on the board, with pictures and illustrate your mechanisms, your causes, then you're an irrational individual. You don't have a theory to present. But they say, look, we can describe what Father Universe does. We represent him because he talks only in the language of mathematics. No, he doesn't. Father Universe never went to school. He doesn't know anything about math. He moves atoms from one place to another in every frame of the universal film. And what these people have to do is explain the mechanisms. If they cannot explain the mechanism, they don't have a theory. Description, a mathematical description, is not a theory. Period. We're done. These people call what they do theories. They don't do theory. The theory part is the explanation, and those are all irrational. So none of those are valid in science. So they don't have a theory. Quantum is not a theory. Quantum is a statistical description of what they think is in there, based on the assumption that what they think is in there are particles, discrete particles, which ain't particles either, because they acknowledge that those are not corpuscles. They're not little grains of sand. What they're staring at, or they think they're staring at, when they go to the lab, is all these values. They think they're looking at particle, a little discrete particle. At least that's how they represent them. But of course, they cannot make sense of that. They cannot make sense of what they think is in there, because they don't see it. It's not like they see it. It's like they assume that what they're staring at are a bunch of particles. And so they just mathematize it. They talk about energy, mass, charge, force, field. And they say, look, the field moved this way, vibrated, here's the particle. When it ain't a particle, here's a force, which ain't a thing, right? Mass, it ain't a thing. Energy, it ain't a thing. None of those are things, but that's what they introduce as things into physics, into mathematical physics, or into the scientific environment. And that's where we get lost. That's where we have irrationality. So the only thing coming out of mathematical physics is irrationality. They're using the wrong tool, which is math, to explain their theories, if you can call those explanations or theories. And that's what people believe, and they just regurgitate what these people are saying. And that's the world we have today. That's the state of the art of mathematical physics. And in relation to quantum mechanics specifically, because they can't see or touch any of the things that they have in there. So they think they're colliding particles, and you say, you mean two particles collided? Well, a particle is just a number, just the energy, which we call mass, because according to Einstein's equation, energy and mass are the same thing. And so they're colliding energies, they're colliding masses, kilograms or electron volts or whatever they're colliding in there. And they say we collided particles. And people say, okay, the two little balls hit each other. No, that's not what they did. They accelerated whatever they accelerated at a certain energy. They collided these things, whatever it was that collided, and then they represent all that with mathematical concepts. And that's why we have a big problem, because we don't have physical entities in front of us. There are no physical entities in all of mathematical physics. Okay? Okay, but let's get on to the subject matter today, the main course. And what is that? That's the electron. Well, let's do a little bit of history. How did this idea of the electron ever come into being? I mean, we had Dalton, which was probably the first guy at the beginning of the 19th century who came up with the notion that, that there's this atom. He had no idea of the electron at the time. It was the beginning of the 19th century, and he essentially picked it up from Democritus. He said, look, I'm going to classify all these elements in terms of atoms, okay? And so he said the world out there, the invisible world, is made of atoms. So that idea was more or less maybe in the right ballpark, you could say. Same for Democritus. You know, there's all these particles out there. Okay, no problem so far. That's a good start, I would say, okay? And so by 1857, we have this fellow. He's a German fellow. His name is Johann Geisler. And he created this tube, the Geisler tube, you could call it. And that one's from, I think, 1861, 1862. That was not the first one, but you get an idea what it is. You have two electrodes. You have electricity going through there. And he had a gas in there, and so it lit up, you know, like a fluorescent tube. And so he was stunned by that, and once he created this device, everybody started using it and modifying it as time went by. By the time you get to, well, just a few years later, in fact, a couple years later, you have some people, one of them who worked with Geisler, and it was this Julius Plucker, and he created the Plucker tube, you could call it, right, 1859. Another German, Johann Hittorf, and he came up with a different kind of tube. They kept modifying these tubes, and one of the big improvement was done by William Crookes in England, and what he did was he created a higher vacuum. And by creating the higher vacuum, he was able to make like a pencil beam, and they were able to study the atoms or whatever was happening in there in a little more detail. Okay? So these things kept improving over time, and you get to this fellow, a French fellow, he's named Jean Perrin. 1895 showed that cathode rays were of negative electric charge in nature. What did he mean by that? Well, the electric charge, the negative electric charge, that negative and positive was created by people like Benjamin Franklin, who just assigned labels to opposites. He said, look, this one's positive, that one's negative, positive attracts negative. That's all that Perrin essentially said. Okay. Now, one thing Perrin also mentioned, this was in his lecture of 1926, his Nobel lecture, he said, I believe, the first to assume that the atom had a structure reminding to that of a solar system where the planetary electrons circulate around the positive sun. So he came up with this planetary model of the atom, saying that, look, I think that all these electrons, these negative electrons, they're going around like planets go around the sun. So he came up with this notion, he said, and he says that Rutherford gave him a little bit of credit, okay, in one of his talks. So apparently this solar system type atom starts with him. If that's true or not, well, I don't know. Only Mother Nature knows what really happened. But he claims that he's the guy who came up with that. And you get to Thomson. He's famous for his plum pudding model. And he was the first to show that, you know, these little electrons belong to the atom. They were part of the atom. Okay, until then, they didn't really know what these electrons were. They had this notion that maybe these electrons went around a nucleus with a planetary model. Thomson, I guess, you know, by the time he comes up there, he said, look, you know, I think these electron beads, he was convinced they went from negative to positive, right? So he said these are negative beads because they go to the positive pole, right? So again, just opposites, just labels, that's all they were. And he said, look, I think those little beads are part of the atom. But then he had this notion of what the atom looked like, and it was like the plum pudding. He said you have this massive positive base, and all these little electrons are embedded in there, okay, these negative electrons. So yeah, it says 1897, Joseph Thomson measured the mass to charge ratio of the electron, and that allowed him to make the electron a little discrete little bead, right? Thomson showed that the electron is a particle with a mass and a charge. Its mass to charge ratio was much smaller than that of the hydrogen ion H plus, right? Therefore, the electron is a tiny particle that is part of the atom. Okay, so at that point they started, turn of the century, that's when they started getting the idea that there was this little thing called an electron, like a bead. And then the question is, what was the shape of the atom? Was it, again, like Thomson suggested, that it was a cake with all these plums embedded in them? Is that what it was? Or was it like a planetary model, right? And here you have a fellow, his name is Veritasium, what's his name? Can't remember his name right at the moment, but Derek Muller, that's his name. And he essentially summarizes that for you, okay, in a chat he has with another fellow. So listen to him, he's going to summarize it for you. Here goes.
What's producing this glow here?
There were two main camps. One thought that it was waves, and the second thought that the electricity was being carried by a stream of charged particles. Well, it was J.J. Thomson in 1897 who came up with the idea that there is a stream of very small charged particles, negatively charged. They're smaller than an atom. So the smallest atom, hydrogen atom, they're about 1,000th of the size of that. This electron, as it was known, is what's carrying the electricity.
So Thomson came to the conclusion that all atoms have this particle as one of their constituents.
That's right, that's right. So it wasn't a billiard ball, there had to be something inside the billiard ball.
Okay, so we have now this electron bead, turn of the century. Again, they were just trying to figure out what an atom looked like. We have the electron, it looks like a little bead. And the question is, how did it fit within the atom? What did an atom look like? Okay? And eventually they come up with this notion. Einstein thought that the electron was some kind of a bead because we have a photon that would hit the electron, knock it out of its valence band, you could say, and all these electrons flowed because of that, and that flow was electricity. That was the notion that was developing. And here you have an image of that, Einstein thinking that, electrons were simply little beads that were hit out of polished metal plate when a beam of photons hit it. So they were thinking of electrons as little discrete beads at the time. They just didn't know what the atom looked like. Remember, this is the photoelectric effect. The explanation for that by Einstein was in 1905. So they were still developing the notion of the atom. They didn't really have an idea. They had the planetary model in their heads, but again, they didn't know how it all fit together. And well, we arrive at today, and we know from what we see out there what the electron bead really represents. And here it is. This is from, I think, from the AI. It says, each atom consists of a positively charged nucleus surrounded by a number of electrons. This is finally what the final model, right? Electrons are bound to the nucleus. Doesn't say how they're bound to the nucleus. I mean, are they attached? It says it's bound, but bound by what? I mean, by air, by ether, what's binding it? And highly mobile electrons are responsible for high electrical and thermal conductivity in metals. Electrons can escape from their atoms and materials, and as free electrons form particle beams in a vacuum. So they have this notion that the electron is a little bead. I mean, this is what they finally came up with. And this bead, for some reason, for whatever reason, just leaves the atom, and they start flowing as a bunch of electrons, which is what they consider as electricity. The flow of all those red beads, that's what everybody understands by electricity today. That means the electrons are leaving their atoms and just flowing. Okay, this is the notion we have today. And the question is whether this has any validity, because you cannot justify that atom. You cannot say why it is that the electron first doesn't fall all the way to the nucleus, because the nucleus is positive, the electron is negative. We're done, right? It should be falling right in there. It should be hitting the nucleus. And that's not happening. You know, the electron just keeps bouncing back and forth between energy levels or orbitals, right? And then for some reason, it decides to leave, you know, and again, we don't know what's forcing it out of its energy level. And it's going out of the energy level and forming all these sequential dots, these points, particles, corpuscles, and they flow, and they call that electricity. The flow of all those little beads. And then they tell you, well, it's not a bead. It's just a quantity. Okay, so they're not talking about things again, they're talking about quantities, you know, charges. That's what they call them. And so this is the notion they have today, okay? Here you have it. The one on the top shows the electrons flowing from atom to atom. But what they've done over the years is they got rid of the atom. They don't need the atom anymore. Now they have all the beads, like you see at the bottom there, just the beads flowing. No atoms, okay? And so electricity is just a flow of electron beads. We have a problem with that because, you know, now we don't even need the atom. We can have just all these beads flowing for whatever reason. And they don't form part of any atom while they do so. And you'll see, like, especially the people from the electric universe, they picked up on that, and they say that all those filaments that we see out there in the universe, right, they look more or less like this. All those filaments that bind every galaxy and star out there, that's the flow of electron beads. And so what are those electron beads flowing through? Are they going from atom to atom? Are there atoms from here all the way to the other galaxy? And all the beads are just flowing from atom to atom? And then what they do is they do the same thing as the establishment. They get rid of the atom. And they think electricity is just a flow of electron beads. And all these beads are flowing from one galaxy to another through empty space. What forces them to go from one star to another, let alone from one galaxy to another? These beads just flow. Nothing interrupts their flow out there. Why would they flow in a given direction? Why would they flow in a straight line, etc., etc., etc.? There's too many problems with that idea. So the notion the electric universe has, like the notion that the establishment has, that electricity consists of a flow of beads, I don't think so. You know, that's an irrational notion. They cannot justify that. No, electricity is not the flow of electrons. There's no flowing of anything, okay? And that's the issue. The issue is that the notion that we have today of electricity, the one that has evolved, is totally misrepresenting what Mother Nature and Father Universe do out there. And yeah, if you look it up, it says this from the AI: an electron is considered what? To be a point particle, which it ain't, because the word particle is very misleading there. No, it's not a particle at all, because the word particle in quantum mechanics means number. It's a quantity. Okay, so it's a quantum, right? And this means it's treated as an infinitely small. They always make it infinitely small, meaning it has dimensionless entity. Well, infinitely small is not dimensionless. Small is not the same thing as dimensionless. Dimensionless meaning 0D, 0 dimensions, is not the same thing as small. Small means there's something there. I don't care how small it is, it's still small. There's size, there's shape. Dimensionless means there is no shape, no volume, no nothing. And therefore it's not an entity. So we have a problem there, because right there you have a contradiction. It says, meaning it has no internal structure, and its interactions are described, always described, right, and never explained, right, as if it's located at a single point in space. The defining feature of a point particle is that it lacks spatial extension. Well, then it ain't a particle. It's not a thing. If it's got no spatial extension, it's got 0D, it's got no size, no shape, it ain't an object. It's not a thing. A thing is that which has shape. So it can't have no spatial extension. Being dimensionless, again, right, does not take up any space. Again, 0D, that's not an object, it's not a thing. It's the opposite of an object, it means nothing. Literally, okay? However, pun intended. However, the electron's wave-like nature and the uncertainty principle suggest it occupies a volume. So does it or don't it? They have it both ways. They have, on the one hand, they say it's 0D, it doesn't occupy any volume. But then it turns into this wave which covers all of space, and it does have volume. In fact, this has the volume of all of space-time, all the way to the edge of space-time. So suddenly that wave, which is a wave function, right, collapses into a 0D nothing, And when it feels like it, or when the mathematician feels like it, it suddenly expands to cover all of space-time. And we call that a field. What is a field? A bunch of numbers that become weaker away from ground zero. So what have they explained? This is magic. This is not a physical interpretation. This is irrational explanation. Okay, but just in case, they had to invent not only the particle, electron being a particle, they turned it into a wave. And it was this fellow, Louis de Broglie, and he said, theory explained the quantization of energy levels in atoms. Is atomic orbits, electrons are in atomic orbits, electrons are described as standing waves, where the wavelength of the electron fits exactly within the orbit's circumference. And you can see it there. You can see that he sees it as a wave, an integral wave. So, you can't have half a wave. That's what he was saying, essentially. There are integral waves all around. And no matter if it's greater or lesser, the diameter of that hula hoop, right, made of waves, it's always an integral amount of waves. So it gains a link, as we call it under the rope model, or it loses a link. That we can understand. If it's a rope, yeah, you can imagine it gaining and losing a link. But he's talking about waves. He's talking about a hula hoop made of concepts. He's just saying it's a bunch of vectors. And all these vectors are twined around, because he shows them twined around, but he's saying that they have to have integral waves. In other words, the wave has to be an integral. It can't be half an integral or a quarter or whatever. De Broglie's theory explained why electrons in atoms are restricted to specific energy levels. That he explained. He didn't explain it, really describing it mathematically. That's what he did. They call it an explanation. It's not really an explanation, because he's making an assumption that ain't true, which is, that there's this abstraction called a wave that surrounds the atom, and he calls that electron. The whole thing, the whole hula hoop is the electron. Keep that in mind, okay? And the only thing he's saying is that the hula hoop is made of integral waves. It's got to have a certain an integer. It's got to be 1, 2, 3, 4. It can't be 1.5, 2.5, 3.5, or 1/4 or whatever. So he's saying it's got to be integral waves. That's all he did. That's what he won his Nobel Prize for. Okay, just mathematizing the wave. And what is the wave? Wave made of two fields. What is a field? A bunch of numbers. It's made out of what? Vectors, bunch of numbers. It's all numbers. None of that has anything to do with physics. Okay, so here we have the Wikipedia, and it tells us something about the wave-particle duality. Listen to this. Here it goes. It's important to look at how this duality is being manipulated. Listen carefully.
Particles are sent on two slits. The particles touch the screen randomly. A wave is sent on two slits which make it interfere. This results in fringes on the screen. A quantum object is sent on two slits. The wave suddenly reduces into a particle when touching the screen, and more likely at the positions where the wave was more intense. At the end, one observes impacts as for particles, and interference fringes as for waves.
Okay, so now you know exactly what an electron is. It's both a particle and a wave. When they want to explain the electron or describe it, they can't have the particle because that don't work. They can't have the wave, that don't work, so they turned it into a mathematical object. That's what they did. They said, look, it's a mathematical object. And what does that mean? It means it's a quantum object. It it follows the rules of quantum mechanics, meaning it can be anything you want, especially particle and wave. Whenever you need the particle, you use the particle. Whenever you need the wave, you use the wave. That's how simple it is. See, you just go back and forth and you got it made. You can get through your presentation And that's what's accepted by all mathematicians. In fact, if you ask the so-called physicists, right, the mathematical physicists at the stack exchange, this is what they'll tell you about the electron. They can tell you exactly what an electron is. And it's this. There it is. The electron is best described by models that allows both an interpretation as a point charge particle, all right, and as a wave function. Another fellow says quantum waves are waves in coordinate space, but not necessarily in real space. So we don't have it's not real, it's just some kind of wave out there, whatever that is, whatever it's made out of. Another fellow says the electron is neither a point particle nor a wave function. We have condensed our knowledge into a mathematical form that we call a model. The important point is not to confuse the model with the reality. Again, these people are talking about abstractions, reality. What are they talking about? Another fellow says we have no idea what anything really is. The electron is not a wave function. It is modeled by functions of wave equations representing waves in probability space. Okay, math, just a bunch of math. Both point particle and wave are metaphors. An electron is not one of these. An electron is an electron. Oh, great. That's a great definition. It is important in physics to remember that the thing is not the metaphor. Okay, so they're saying it's a metaphor, whatever they're metaphorizing here, because if you're going to use a simile, it better be a simile for something. It's got to be a metaphor for something. And if they're going to use a concept and they're going to replace it with a particle or with a wave, well, we have a problem, because that's not a good metaphor. It's not a valid metaphor, right? And so the point particle is what an electron is. The wave function is where the electron is. So I guess they're concerned more about where and not about what. And then the last one says the theoretical description, the pure shape of the object. I like that, because now they're going to talk about the shape of the object, right? Should be called its avatar. What does it mean to be a point body? The zero vector zero, because we like to center the avatar on the center of mass. Again, they're using a little caricature to put in there, and they say, look, this is going to represent the zero vector. What is a zero vector? Well, it's something with no shape, no size, no volume. That's what a zero vector is. But then if you want your rotational motions to be physically plausible, meaning understandable, right, you have to go through some extra gymnastics. Yeah, you can't have a point particle that rotates. What kind of rotation can a zero-dimensional, no volume, no size thing, if you can call it a thing, how can that thing rotate? What kind of nonsense are they talking about? Okay? So again, keep all this in mind, that what all these people are doing is just using math, and they're trying to represent it with objects, but the objects that they put in there are zero-dimensional, no size, no volume. And then you say, well, okay, and then you have spin of that nothingness. And they say this thing spins. Well, how can you conceptualize spin if you don't have a thing there? So that's why they put the little ball. They say, well, you can imagine the little ball. You put a little dot, paint a little dot on the ball, and you can see the dot going around. You say, okay, I understand spin now. It's that little dot that's going around, right? But you can't put that little dot on a zero-dimensional ball. What is a zero-dimensional ball? Okay, and this is the problem. They have no objects in quantum mechanics. So until we get that straight, we can't even start the presentation. That's the issue. Okay, so what are the problems with the famous electron of quantum mechanics even today? Well, here's a little summary, okay? Fatal problems with the quantum electron. No point of what, no notion of what it is. Okay, we don't have a what. There is nothing in front of us. And nobody has any idea what electron is. They say, well, it's infinitesimally small, so infinitesimally small that it has no dimension, no size, no shape. That's how infinitesimally small it is. And when you say, well, hold it, infinitesimal small is not the same, or forget about the word infinitesimal, that's just misleading. Small is not the same thing of 0D, of nothing, no volume, no shape. Those two are not the same. And they say, well, we can't measure below a certain level. That's the answer to that. So we consider it a zero-dimensional object, and we get away with that. That's what they're doing, okay? Then it says, can't point to an electron image. You can't point to an electron. Whatever you point to, they say, well, that's not our electron. It's a little bead, it's a little dot, but you can't point to it because there's nothing there. It's zero-dimensional, no size, no shape. No definitions or descriptions for electron. We have none. Okay? We don't know what an electron is. In fact, you have here the electron that, according to some Swedish people at a university, they said they filmed the electron. It looks like this. Okay, the electron film for the first time. Okay, says now it's possible to see a movie of an electron. Okay, the movie shows how an electron rides on a light wave after just having been pulled away from an atom. So they're saying this is what an electron looks like. There you see it for the first time. Okay, this comes from 2008. And it says this is the first time an electron has ever been filmed, and the results are presented in the latest issue of what? Physical Review Letters. So here's an electron. And we have a problem, a couple problems. The first one is that's not zero-dimensional. Hopefully what you see in front of you is at least two-dimensional. The other one is you can see some lines there. That means that the electron is made out of little parts because that's what they're showing there, right? So it looks like it's built from smaller parts. So we have at least two problems with that, with the Swedish electron. And on the final issue is that they never got a Nobel Prize for this. You would think that, you know, all these people should get a Nobel Prize for having filmed for the first time the electron. Everybody forgot about them. What is it that they filmed? Why did they put that in the Physical Review Letters? I have no idea. So yeah, they don't have that. Then they have the problem with spin. Here's the spin part, okay? And this is the spinning electron. And you say, well, hold it. I thought the electron was 0D. No volume, no shape. What is it that's spinning? How can you conceptualize that a 0D nothing rotates, spins, whatever spin is, because they never define spin either. And so we have all these contradictions. They use the word spin. They say they illustrate it as spinning of a top, and then they say, oh, by the way, we don't know what spin is, and that's only the first problem. The second problem is we have a zero-dimensional electron that is spinning. You try to conceptualize that. The electron is not an object. Okay, it's just a quantity. Okay, it's a quantum of some kind. Right? They measured the charge on that. Robert Millikan did that. And so they know how much charge it has, but they don't know what it is, what they measure. It's not made of quarks. This is an interesting one because here you have the proton and the neutron. And fortunately, you know, they figured out that these two are made of 3 quarks. In fact, they're made out of gazillions of quarks that come in and out of existence constantly inside the proton and inside the neutron. They had to do that because they had to justify the weight, the mass of the proton and the neutron. Why? Because each one of those quarks weighs a lot less than a proton. And so they said, well, if we add those 3 quarks up for either the proton or neutron, we don't get the weight, the mass of the proton and the neutron. So how do we get the mass? Well, we put gazillions of protons and neutrons in there, and we look at their kinetic energy, you know, all this energy they have in there, and all that adds up to the mass of the proton and the neutron. Okay, let's accept it. Let's concede that nonsense, right? How can we extrapolate that scheme to the electron? Is the electron also made of 3 quarks of some kind? You know, you can put them any way you want. You can put 2 up, 2 down, 3 up, 3 down, whatever you want in there. I don't care. How do you justify that same scheme to the electron? Because what they were trying to explain was the charge on the proton and why the neutron has no charge. Well, the electron has a negative charge, 1.6 times 10 to the minus 19 coulombs. And the question is then, you know, how does that scheme, how can you extrapolate that scheme to the electron? And of course they can't. Okay, so we have a problem because, you know, they created a scheme, right, to explain the proton and the neutron, but they cannot extrapolate it to the electron. So again, you know, is the electron made of quarks also? Why it doesn't fall to the nucleus? They cannot explain that either. You know, and here you have a couple of issues there. Here's the first one. We have why don't the electrons fall into the nucleus? Same reason planets don't fall into the sun. This is what physicist says. The reason is that electrons are not little particles or balls of matter. I like that. You know, they're not balls. They're balls when you want to illustrate, but then they're not balls. Okay? They have significant energy, bunch of energy. What the Feynman says, we don't have the slightest idea what energy is. Normally, they do not interact with protons, right? They better not, because one is negative, the other one is positive. They interact, they stick together, right? However, it does sometimes happen that an electron is captured by a proton in the nucleus and converted into a neutron. Okay, so we have a proton and two balls, right? A big ball, bowling ball called a proton. We have a little bead, little grain of sand called the electron. It's stuck to the proton, right? And that's what a neutron is, a big ball with a little grain of sand stuck to it. Is that what a neutron is? They're looking at, again, charges. That's all they're looking at. And because one is positive, the other one is negative, so the charges, neutralize each other, and that's why we have the neutron with no charge, right? Concepts that are close enough in the everyday world are not close enough at the subatomic level. Yeah, the problem is that concepts are not close or far away. Concepts have no locations. So to say that a concept is close to this other concept, love is close to intelligence, well, I don't know. How close is it? And so we have a problem because they cannot explain, again, why the electron doesn't fall to the nucleus, one of the questions they set out to prove at the beginning of the 20th century. And of course, they cannot explain also why it doesn't fly away. Okay, so we have a problem with both situations. Neither one of those situations has ever been explained. And why it doesn't fly away. Electricity, the flow of charges. What is that? What do you mean the flow of charges? That's a measurement issue. You measure, you say so much charge has flowed through this point here. That doesn't tell me anything about what a charge is, or what's carrying the charge. That's what they haven't answered. Okay, is there a little ball there that has a little charge in it? And what is this charge? It's just a measurement. That's all it is. So they don't have a physical model of any of this. There's no physics in mathematical physics, let alone in quantum physics. And they have also this situation where the electron goes through the p orbital, because first they say, look, you have the electron, it's negative, right? And it gets close to the proton, but not close enough, because it's always in this energy level, in this orbital, and for some reason it doesn't fall all the way to the nucleus. And so they explain that after 2 hours, right? And then they tell you, look, by the way, it does go all the way through the nucleus and out the other end. And here this is how they illustrate. They have these p orbitals, and those little white beads that you see there going around, those are the electrons. And they go right through the proton in the p orbitals. We can all understand the s orbitals, the round ones, right, the circular ones. How do you explain now the p orbitals where the electron bead goes right through the proton center, the positive proton center? Don't they get stuck there? And so they have all these contradictions, and they just live with all of them. They never explain these away. They live with all of these things. They accept them, and they say, well, all we do is math. We don't do physics. Then don't call it physics. If you want to do math. Don't bother me. So we have all these problems. We have also that electricity is the flow of charges, and again, I showed that earlier there, where you have these electron beads. They call them charges, and the charges are flowing. It used to be that the electron, Einstein explained that the photoelectric effect, the beads apparently go from one atom to another. Well, they got rid of the atom, and now all we have is the flow of beads. So there is no more. We don't need the atom anymore. We can have just the flow of electron beads and negative charges flowing through the air. Okay? So we don't need the atoms to flow anymore. And then, we have also, give me a second here. We also have give me a second here. Let me get this out of there. And then we also have the quantum jump, the fact that the electron bead jumps back and forth between orbitals, right? And the question is, what compels an electron bead to fall and to rise? Why does it do that? What's the explanation for that? Is there a physical cause? Is something hitting the electron bead, forcing it out? Is something hitting the electron bead, forcing it in? And that's when they introduce the word energy, and they say, well, let me tell you about energy, which we don't know what it is. And so here you have this quantum jump. This is what it looks like. Okay. Essentially, the electron bead falls from one energy level to the other. When it falls, it releases energy, whatever that is. When it rises, it's because the atom absorbed energy, whatever that is. And again, they have that electric current where the electron beam goes from atom to atom, but then they get rid of the atom as well. And so, we don't have any explanations for any of these mechanisms. There are no mechanisms in all of quantum mechanics. So when people ask, they ask qualitative type of questions. You want to know what gravity is? You say, okay, why does this fall to the floor? I don't need any math to answer that question. Okay, I should say, look, this is what's causing this to happen. And you can say something's pushing it, something's pulling it. You can say whatever you want, but we don't need any numbers. We don't need any equations because we're asking a qualitative type of question. And the same thing happens to the electron. Why does the electron fall to the nucleus, to the positive proton? You got to give me a qualitative explanation. You cannot say, well, it's all this energy. Energy is not going to explain the thing because energy is the phenomenon, because energy is just a quantity. Could be electron volts, could be whatever whatever unit set you're going to use, and that doesn't tell me the cause, what's preventing the electron from going further beyond the energy level and falling all the way to the nucleus. And the same thing, you cannot explain why it doesn't fly away. So, when you have this quantum jump, you can't, they don't have an explanation for either one, for why it doesn't fall, why it doesn't leave the atom, for the electron. And so we have no explanations, and people are asking these questions, these qualitative type of questions, and quantum to this day, after 100 years, has no answers to that. And I think they ran against the wall now. They're at the end of the line because now there's no more equations to do for quantum mechanics. I guess all the equations ever imagined are there. So is at the end of the line we say, well, we have all these equations, we have all these descriptions, but we can't explain anything. And that's the state of the art today of quantum mechanics. And that's why some people, are saying, well, we got to change something. We got to wipe all this out or come up with brand new ideas, because right now we have no answers to any of these questions. And we're at the end of the road. They painted themselves into a corner. They have no answers to questions that people ask. And so the question is it the end from quantum mechanics?